Hey guys, today we're going to start talking about some basic concepts that we need to be able to learn about physics. So, these concepts for today are going to be the first one that all motion is relative, which is a very large scale idea and pretty fundamental to everything that we do. Then we're going to distinguish between speed and velocity, and that will lead us into a discussion of things called vectors versus things called scalars. And then finally, the concept of instantaneous versus average value. So we'll start off with this idea that all motion is relative. And by the way, when I do slides like this, generally the objective is one of the objectives that's on the study guide. So you can kind of compare and see where we are in the series of things. Anyway, so this idea that all motion is relative. Now, to start off, let's consider these two passengers on this bus. And the bus is driving down the street. We're watching it go by, like this alarming looking person with the axe is seeing the bus drive by him. When we talk about these two passengers, we say, are they moving? Are the passengers moving? Okay. And I want you to think about an answer. Is the answer yes, they are moving, or no, they're not moving? Okay. Now, most of us will say, especially with this setup, that yeah, they're moving because the bus is moving and they're in the bus, so they're moving. But what if we asked one of the passengers about the other passenger? So this passenger is sitting here looking at this person over here, and we say, hey, is she moving? She'll probably say, no, she's just sitting there. Likewise, this sullen looking youth up here on the second floor, if he looks down at these two and said, nope, neither one of them is moving. Now, they're all correct. We are correct in saying that they are moving because they're in the bus and they're driving down the street. And the passengers themselves are also correct in saying they're not moving. And the reason that we can all be correct is because we are comparing their motion to different things. All right. The idea that all motion is relative. When we say that something is moving, we have to define relative to what. So, for example, we say that they're moving because we're seeing the truck rolling down the road and we consider the street or the ground, the earth, to be stationary. And since they're moving relative to the road, we say, yep, they're moving. Whereas when they're sitting in the bus, their frame of reference is the bus itself, and the seats are not moving. They're bolted to the floor, and they're sitting in the seats, so they're not moving relative to the seats. So when this passenger looks at this passenger, says, nope, she's not moving because she's just sitting there. And the fact that they're rolling down the street is kind of irrelevant because they're just wondering how close together they're getting. Okay, now, what if this kid starts walking, say, toward the back of the bus? Okay, he knows that his bus stop is coming up. He's going to have to get off soon, so he gets up out of his seat. He starts moving toward the back of the bus at 2 meters per second. Now, my question is, how fast is he moving? All right, so see if you can come up with two different answers for this. The question is, how fast is he moving when he gets up out of his seat and he starts moving toward the back of the bus? 2 meters per second. All right. Well, the first thing is it depends, as we say 2 meters per second, but 2 meters per second relative to what? And reasonably speaking, it would be relative to the bus. So he gets up out of his seat, he starts walking, and 1 second later, he's 2 meters away from his seat. And 2 seconds later, he's 4 meters away from his seat. So he's moving at 2 meters per second relative to the seat that he was sitting in, or relative to the bus itself. So you could say correctly, he's moving 2 meters per second, and he's moving 2 meters per second toward the back of the bus. But you could also say, well, we need to take into account the motion of the bus itself, and the bus is rolling forward at 3 meters per second. So the bus is taking him to the left at 3 meters per second, and he's moving to the right at 2 meters per second. And when you put those together, we find out that he's actually moving to in the direction of the bus at 1 meter per second. So he's still moving from our right to our left. He's just not doing it as fast. And he's basically the bus is going past him. He's kind of staying still. Now, if he sped up a little bit and he was going 3 meters per second toward the back of the bus relative to the bus, then he would just remain stationary while the bus was moving past him, and he'd just be staying right there. And then when he gets to the stairs, he can walk down the stairs and a disembodied head falls on the street and we all scream. Um, let's see, let's put this back here where it was before. There we are. Okay, so to kind of sum this up, all motion is relative, and it is meaningless to say that anything is moving except relative to something else. So if you were the only thing in the entire universe, there was no stars, no planets, no nothing, you were just floating in empty space, it would be meaningless to say that you are moving because there's nothing there for you to move relative to. There's nothing for you to move toward or away from. If you're the only thing around, motion, the whole concept is motion is meaningless because all motion is relative. And depending on our frame of reference, we can define objects' motion differently. It just, if we, again, to sum this up, if we consider the roadway to be the stationary and everything is moving relative to the road, we would find this little kid moving to our left, as even though he's making progress toward the back of the bus. If we consider the bus itself to be stationary, then he's moving backwards. He's moving to our right relative to the bus. And interestingly enough, the road itself is also moving to the right relative to the bus. It's as if the bus is stationary and on a treadmill and the roadway is zipping toward the back of the bus as the wheels just spin in place. Okay, all motion is relative. Now we'll get to the idea of speed. And what is speed? Now, you're familiar with this one. This is why I start with this one, because you talk about speed all the time. And generally, when we mention speed, we talk about, let's see, is this the one? Yeah, we'd say describe a speed as like 30 miles per hour, how fast you can drive a car. So when we do this, we say 30 miles per hour. We always speak of it in terms of some distance divided by some time. So MPH stands for miles per hour. And you probably remember from your math class that per means division. So miles divided by hours. Now in physics, our normal unit of measure, excuse me, our normal unit of measure is meters per second, but you're more familiar with this one, so this is a good place to start. So if you were driving and you made it 30 miles and 1 hour had passed, you could describe your speed as 30 miles per hour. Now, relative to what? Because we just said that all motion is relative. Normally, our frame of reference is the Earth. We consider the surface of the Earth stationary. So we would be going 30 miles per hour relative to the surface of the Earth. Now, keep in mind, though, that if you have a different frame of reference, then the surface of the Earth is not stationary. For example, we could consider the sun stationary, and the Earth is hurtling through space going around and around the sun, in which case the surface of the Earth is moving really, really fast. Or we could go a little closer to home and consider the center of the globe to be stationary, and the surface of the Earth is going around and around it as the Earth itself rotates. We could also talk about the center of the galaxy being stationary, and in that case, the Earth, the sun, and the Earth, the entire solar system, is moving, thousands of miles per hour. Yeah, thousands of miles per hour, thousands of miles per minute, really, through an empty space. So it all depends on our frame of reference. But our normal frame of reference for most of what we do is the surface of the Earth. And if it's something else, then we need to define it and mention it. We have to say such and such a speed relative to something else. Okay, so we put this in an equation, and this is the first time I get to show you an equation here. So this is called the speed equation. All right, normally I would write it out for you, but it's just very difficult to do in this format. So please write this down. You want to have these things in all the equations in one place for easy reference and what they represent. So the equation is V is equal to D over T. D is stands for distance, and that's always measured in meters in physics. T stands for time, and that is normally measured in seconds. So we're taking meters and we're dividing them by seconds, and that means that the units of speed is meters per second. Okay, and that is so. These are all things that I want you to remember. I want you to know this equation. We use it so often that I want you to have it memorized. V equals D over T. And you definitely have to know the units of all of these items. So distance is always in meters, time is always in seconds, and most importantly, speed itself is the units are meters per second. Units are really important in physics. They help keep you on track when you're solving problems, and they help you understand concepts if you can remember the units. Pause it if you haven't already. Write this down, make it neat, put it someplace, leave yourself room where you can write other equations on the same page so you'll have them in one place. Okay, speed equation, P equals d over t. All right, let's apply this. Let's use this for a moment here. I'm going to move this up a little bit. There we go. Okay, so suppose we have a baseball that crosses home plate in 0.01 seconds. And the home plate is 0.3 meters wide. We want to know how fast the baseball is moving. So I'm going to show you how to set up a problem like this, and then we'll work through it. Now, this one is simple enough that you might be able to do it in your head or visualize it in your head, but that's why I want to show it to you, is so that we can show you with a simple example to use before you get to more complicated ones. Okay, so we said that home plate equals 0.3 meters wide, and the ball crossed the plate, crossed in 0.01 seconds. Okay, so this is the given information, the information that we were given for this problem that we're trying to do. And you always want to write that down, and it's a good idea to write a G for given, the given information. Now we also want to write down an F here, and this is for find V, which is the speed. That's what the problem is asking us to solve. And as part of this, we always want to write down the units that we want to have the answer in. And since speed is normally in meters per second, we remind ourselves it's going to be meters per second. Okay, next we do an E, which stands for equation. And this is the equation or equations that we're going to use to solve the problem. And in this case, we're going to use the speed equation, which is V equals d over t. Now, if you don't happen to have that memorized, that's why you go to the sheet of equations that you've written down. Because very often, you'll look at a problem and you say, well, how do I solve this? And you basically pull out your toolbox, your sheet of paper with all the equations on it. You can kind of go through them and say, well, this one work? Well, yes, it will, because I have enough information to fill this equation. This one over here won't, because I don't have enough information for all the variables. Anyway, we have our equation, which is V equals d over t. And then finally, we do the work. Okay, W stands for work. And what we do is we substitute our given values into our equation. So we can kind of think of this equation as a template or a jig that has spaces in it that we can put tools and pieces into to hold them together to solve it. So we want to fill in these blanks basically in the equation. So in this case, okay, V, we don't know velocity or speed. That's what we're trying to find. So we're going to leave that as a V. Now it equals. Now how about D? That's the distance. And the distance in this case is 0.3 meters, 0.3 meters. And we want to leave the units attached to the number. No naked numbers in science, especially not in physics. And then we're going to divide that by the time, which is 0.01 seconds. And again, we leave the units attached to it. Right? Now we can just do the math. I don't want to get under my picture here, so we'll just do it right underneath. And we'll get out a calculator and we'll say 0.3 meters divided by 0.01 seconds. And we get 30. And the units are meters divided by seconds, because we have meters in the numerator here, seconds in the denominator. So the units that will drop out of this are 30 meters per second, and that's going to be our speed. Now, we always do a last check here to make sure that the units that we got are the same as the units that we wanted to get. All right. The way we set up our units, 30 meters per second came out of it. That's what we wanted to get, so we can be pretty sure we set everything up right. Okay. And the last step, we always want to put a box around our final answer.